Recording started.
Okay, so we are going to do some stuff from section 10.3. And so, okay, just about set here. Okay, so the first homework problem that I've assigned from this section is problem number 5. And we're looking to find the dy dx and d squared y dx squared, find the slope and concavity if possible at the given value of the parameter. So the first part is analytical, the second part is just plugging stuff in. So in this case, problem number 5 has that x is equal to 2t and y is equal to 3t minus 1. And we know that dy dx is just going to be equal to dy dt divided by dx dt. So let's go ahead and calculate those. dy dt is 3, and dx dt is 2. So we get 3 from here and 2 from there. So the ratio of those two is 3 halves. So that's the slope. And it turns out that we find this as an equation. It's a straight line. The straight line has a constant slope. So as far as the second derivative is concerned, we know it's 0, but how do we know that? Well, what you would do is you would take the derivative with respect to t of, and so let's, if we can't remember what that is, and we go into the book, and d squared y dx squared is dt of dy dx, which we just calculated, divided by dx dt again. So if we take the derivative of dy dx, which is this, with respect to t, well, there is no t, so you get 0 for this part. And then dx dt is 2, so we get 0, which we already knew. And so the slope is 2, the concavity is 0, and it's going to be a constant. Actually, the slope is 3 halves. And and it says find it at point t equals 3. Well, it doesn't matter. It doesn't matter what t is equal to. You get the same slope and the same concavity. So we could say at t equals 3 that the slope dy dx equals 3 halves, and the second derivative, d squared y dx squared, is just equal to 0. And that's it. That was an easy one, wasn't it?
Recording started.
This is problem 8, section 10.3. So it's similar to 5, just a little more complicated expression, not that much more complicated. So again, what we're looking for is the slope, which is dy dx. And relative to parametric equations, we take the ratio of dy dt to dx dt. Again, the dt's sort of cancel out in a rough sense. And so what is dy dt? Well, y is 2t, so the derivative of this with respect to t is just 2. And dx dt, we take the parametric equation here, and so we'll get 2t plus 3. So the slope at any point in the time parameter t is the ratio of dy dt, which is 2, divided by 2t plus 3, which is dx dt. So specifically at t equals 0, dy dx, sorry, dy dx is equal to, so you just plug t equals 0 in there, so you'll just get 2/3. Okay, the second derivative d squared y dx squared, which relates to the concavity. And, you know, it's probably going to be concave up because this looks like a polynomial of some sort. So it wouldn't surprise me if this is a positive number. But anyway, so what we do is we take the derivative with respect to time of dy dx. This is a function of t, and we divide by dx dt. So if we take the derivative of this dy dx with respect to t, what we're going to have is, if we rewrite this, it'll be 2 times the quantity 2t plus 3 to the minus 1 power. So when we take the derivative of that, we'll get negative 1. And actually, it could be, well, yeah, anyway, I was going to say concave up, concave down. Well, let's see what happens. So we get negative 1 from here times 2 times 2t plus 3 to the minus 2 power. And I guess that's it. And trying to make sure, oh, I have to divide by dx dt, which we've already done. 2t plus 3. So I have 2t plus 3 to the minus 2 power, and if we take that to the denominator, we'll end up with negative 2 divided by 2t plus 3 quantity cubed. And so at t equals 0, we actually get a negative number, so that's somewhat surprising. The second derivative will be negative 2 divided by, if you put t equals 0 in there, you'll get negative 2 over 27, which is concave down. So let's, just to convince ourselves that we didn't make a mistake, or if we did make a mistake, to confirm that we did make a mistake, what do we have here? Let's solve for the parameter t. So if you solve for the parameter t, you'll get y is equal to, or t is equal to y divided by 2. And then we plug that in here. So we get x is equal to t, which is y over 2, quantity squared, plus 3 times t, which is y over 2, plus 2. So we'll get x squared over 4 plus 3y over 2 plus 2. Let's multiply everything by 4, so we'll get 4x is equal to y squared plus 3y plus 2. And the reason I was confused or mistook what I thought was going to happen is you can see this is going to be a parabola that looks something like this. And so depending upon whether you're down here, this would be concave up. If you looked here, it would be concave down. So where are we on that particular curve when t equals 0? If you're interested, stick around. What we're going to do is I'm going to open up the graphing program and we'll look at that. And we'll just look at the parametric equation. So, okay, so I've got the graphing program running now. So let's open that up. There it is. Two-dimensional equation. That's parametric. So f of t, which is x is equal to t squared plus 3 times t plus 2. And the y coordinate is 2 times t. And we want to see what's happening at t equals 0. So let's go from negative 1, t equals negative 1 to positive 1. And we'll put an arrow at t equals 0 so we know exactly where we are. So we have t squared plus 3t plus 2t. Okay, so you can see that it is, like we said, it is like a parabola. At t equals 0 is right here. And so this is concave down. And so it does agree with what the actual graph is. Now, if I were to edit this, and if I were to go, say, from t equals -5, and I zoom out, you start to see what it's starting to look like. It's looking like a parabola that's rotated 90 degrees. Okay, so let's go back. That may be all I have to say, but let me just look at the okay, so you saw it look something like that. I just guessed in terms of where it intersected things. But when we came down here, we got a negative sign, which indicated the concavity was negative, which meant that it was concave down, which it ended up being.
Recording started.
Okay, this is problem 11, chapter 10, section 3. And if we look at this, we might recognize that it's a hyperbola with a center at x equals 2, y equals 1, because this, excuse me, because this is the tangent is on the y term. I think it's going to be a hyperbola that is going like this direction instead of one that's going sideways. So I think we have a vertical transverse axis. But we'll plot it later just to prove that that is the case. Okay, so just like the previous two problems, dy dx is dy dt divided by dx dt. So our parametric equation for y, which is a function of t, is the derivative of the tangent. Derivative of 1 is 0, derivative of the tangent is the secant squared of theta. And dx dt, the derivative of the secant is secant tangent. So if we plug that in, we'll get secant squared theta divided by secant theta tangent theta. And the secants cancel out, at least one of the secants cancel out, so we get secant over tangent. And we might be able to, let's bring that down here, we might be able to simplify that further by having secant is 1 over the cosine, tangent is sine over the cosine, so the cosines cancel out, and so we get 1 over the sine, which is the cosecant. We might just use that one. So at pi over 6, theta equals pi over 6. So let's go down a little bit. So what is the slope of the trajectory dy dx at theta equals pi over 6? So we just plug it in. So that's 1 over the sine of pi over 6. Sine of pi over 6 is 1/2. So we get 1 over 1/2, which is 2. Okay. Sine of pi over 6, how we get that is, in the unit circle, you got pi over 3, pi over 6. The sine is the y value. And we always go 1/2, square root of 2 over 2, square root of 3 over 2. So because I knew this was going to be the y coordinate, was going to be the half part, which is how I got that. Okay, so that's dy dx. To find the second derivative, which is the concavity, which is d squared y dx squared. You take the derivative with respect to time of dy dx divided by dx dt. So we take the derivative of dy dx. What is dy dx? Well, it's the cosecant. And the derivative of the cosecant, I think, is negative cosecant cotangent. Not 100% sure, so we could go to the front of the book, which has a list of things. So the derivative of I'm taking this thing, I'm using this version, cosecant. So the derivative of the cosecant is negative cosecant cotangent. So we get negative cosecant theta cotangent theta. And we divide by dx dt. Dx dt was equal to the secant theta tangent theta. Okay, so what the heck does that all mean? Well, probably the best thing to do is to put it in sines and cosines. So you get 1 over the sine of theta for the cosecant. The cotangent is cosine over sine. And we divide by the secant, which is 1 over the cosine. And then we multiply by the tangent, which is the sine over the cosine. And we can take the reciprocal of these and multiply them, get them all in one level. So we have the numerator. And then we're going to take the reciprocal of the denominator. So we get cosine of theta over 1 times cosine of theta over sine of theta. And is that all right? Yes, okay. So we get negative the cosine of theta over the sine of theta, and the whole thing is cubed. And so that's negative 1 over the tangent of theta cubed. And so what is the tangent of pi over 6? Well, if you remember, it went 1 over the square root of 3. That was pi over 6, 1. And the square root of 3 over 3 was for pi over 3. So this is the one. So we'll end up with negative. And if we're just looking at the sign, we've got the negative sign, and this is going to be positive because this is positive. So, but to get an actual number, we'd have 1 over the square root of 3 quantity cubed, which would be negative 1 over, well, square root of 3 cubed is 3 times the square root of 3. And if you multiply by the square root of 3 in the numerator and denominator, you get negative the square root of 3, and we'll have 3 times 3, which is 9. So that's the second derivative at pi over 6. But it's negative, which means concave down. So let's give it a try. So let me go. I'm going to have to make sure I get this thing typed in correctly. So we're going to go to the graphing program, and we're going to edit the parametric equation to put the completely new parametric equation in, which is number 11. So it's 2 plus secant of t, and y is equal to 1 plus 2 tangent of t. And we're going to let it vary between 0 and 2 pi, which is 6.29. And what we're looking for is actually the arrow. We want it evaluated at pi over 6, which would be 3.14159 divided by 6. Hopefully that works out. Okay, so there you go. It's a hyperbola. Actually, it's pointing this direction. It's going the opposite of what I thought it did. I guess if we go back to our previous example, we'll see that was right. If you go to problem 42 in section 10.2, it's secant in x and tangent in y, which is this kind of hyperbola. So it's the other way around. Okay, now here's the point. So what do we see the slope was? I have to go back and look at it. So if you wrote it down, it said the slope was equal to 2, and the concavity was negative. So it's saying right here the slope is 2, which looks pretty close to 2. If you go over 1 and up 2, that would pretty much match a slope of 2. And the concavity is, see how it's bending this direction. So the inside of the curve is that direction. and therefore it's concave down, and therefore it's correct. So let's go back to the smartboard. And we got it all worked out. There's the slope, 2, positive 2, concave down. So it's fairly complicated, but we took the derivatives, dy dt, dx dt. We came up with the ratio of the trig functions. Then, so this was dy dt and dx dt. Actually, it's dy d theta and dx d theta. Should have done that, but hopefully it didn't confuse you too much. We simplified this by substituting in the trig functions for the original, for these, using trig identities. We got the cosecant of theta, which is 1 over the sine of theta. The sine of pi over 6 is a half, so 1 over a half is 2. That was the slope. And then we took the second derivative, which was this one. And I'm going to just look in my answer book just to make sure there's no doubt that I did this thing correctly, because it is much more complicated than the other ones. So what do we got? Section 10.3, number 11. Okay, yeah, okay, I found one little error. I wrote the problem down wrong. There's actually 2 t tangent theta. Okay, so that should be 2, which would affect this number. This would actually be 4. And this thing down here is would have another 2 in it. So it's so the procedure is correct, and I'll hopefully you will have read the description in the problem that corrected that ahead of time.
Recording started.
Okay, we're at problem number 19, and we're only doing parts A and C. We could actually calculate, we have to calculate dx dt, dy dt, and dy dx anyway, without using graphing utility. So, let's go ahead, excuse me, what was that? Let's go ahead and do it. So, to be able to plot the, well, we'll plot the graph in a second. We'll do part A last after we figure out all this information. So, we need to dy dx, which is the slope, because we're going to use the slope, point slope form. So we get dy dt for the numerator, and we divide by dx dt. So let's calculate each one of those. Dx dt, so we take our equation for x, we take the derivative of the right-hand side with respect to t, and what we get is 2t minus 1. And dy dt is equal to 3t squared minus 3. And so now we can plug in for dy dt 3t squared minus 3, and for dx dt 2t minus 1. The one thing you'll notice about this is if this goes to 0, the denominator goes to 0, the number goes to infinity, or it's undefined. I think it would end up being undefined because this will not go to 0 when this goes to 0. So at t equals a half, we have the function is undefined. Or not, the function is undefined, the slope is infinity. So anyway, so that is the slope. So we could plug in t equals negative a half and find out what the slope is. So dy dx at t equals negative 1. We just plug it in there. So we get 3 times negative 1 squared minus 3. And then we have 2 times negative 1 minus 1. So 1 squared is 1. Negative 1 squared is 1. 1 times 3 is 3. So actually we get 0. divided by, we get -2 minus 3, -3. It really doesn't matter what the denominator, the numerator is 0, then it's 0. So we actually have a slope of 0 at that particular point. And so this is going to be a horizontal line. It's going to be y equals whatever the y value is right here. If we went back to, still do the point slope form of the linear equation is y minus y1 is equal to m times x minus x1, where x1 and y1 are just a coordinate pair. So we could find x at t equals -1 by just plugging -1 in there. So we get -1 squared minus a -1 plus 2. So that will be 1 plus 1 plus, so we get a 4 there. And our corresponding y value at t equals -1 is -1 cubed from here. -1 cubed minus 3 times -1. So -1 cubed is -1. And this is positive 3, so 3 minus 1 is 2. So this would be the x and y coordinates. And if we plugged it into this point slope form, well, m is 0 for here. M is the slope. So this whole right-hand side disappears. And so y minus y1 is equal to 0, or y minus 2 is equal to 0, or y is equal to 2 is the horizontal line that represents this tangent line. So let's see if that is true, see if I made any mistakes or not. So let me minimize this. I need to open up the other window so now I can close this and open the other one. Oh, got something wrong there. Shared the wrong screen. Okay, so now we're at where we need to be. So two-dimensional plot, we're plotting a parametric equation. And the original parametric equation was x is equal to t squared minus t plus 2. The second parametric equation was t cubed minus 3 times t. Let's check this out again. T squared minus t plus 2. T squared minus t plus 2. T cubed minus 3t. And we're going to go to a low of -2 for the t. And we'll go to a high of 1, and we'll put an arrow at -1, which is where we're evaluating all this stuff. So there you go. There's the graph. There's where t equals -1. You see we have a horizontal line. So we just have y equals 2, which is the corresponding tangent line at that particular point. So it looks like that's correct. So let's stop sharing it, and we need to open up the smartboard. So there we are. And just to be on the 100% safe side, if that is the right answer, you can just close it. But I'm just going to check the answer book. So it's 10.3, problem 19. So 10.3, problem 19. So we get the slope is 0, y is equal to 2, and we get that equation. Well, one thing I found interesting, and hold on, I'm going to sneeze here. If we go back to the graph and expand the range, let's just see what this curve looks like, because it's not exactly as it appeared. Well, it is what it is. But if I let's see, if I increase the t, so I'm going to go to a t of maybe 4 and see what happens. So that's what it looks like right there. So we're still at t equals 4, p equals -1, x equals for y equals 2. So it has this kind of loop-de-loop shape, so I thought you might be interested in seeing that.
Recording started.
Okay, our last problem in the section is 37, which is asking about concavity, which involves a second derivative. So we just need to find d squared y dt squared. So before we can take the second derivative, we need the first derivative. And we can use this relationship, which we've used quite a few times already, where we rewrite the dy dx in terms of the derivatives of each coordinate with respect to the parameter t. So dy dt, come here, take the derivative with respect to t, we get 3t squared minus 1. Dx dt is just 2t. Derivative of t squared is 2t. Okay, so we have the ratio 3t squared minus 1 divided by 2t. And now what we do is we take the derivative of this in respect to t again to get the second derivative, dy squared dx squared. We take the derivative with respect to time of dy dx, and we divide by dx dt. So this is a quotient rule problem. So let's do that. So the quotient rule is to take the this term, derivative of this term times that term. So the derivative of this term is going to be 6t times the second term minus the derivative of the denominator, which is 2, times the numerator, which is 3t. Move this over. So we get the derivative of this is just 3t. Actually, no, we're not taking derivative of that. We're just taking 3t squared minus 1. So this is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator divided by 2t quantity squared. So that is this part. And then we have dx dt, which we've already done. So let me have a page. So the question does this cube is a cube. Well, if we do this, we'll have 2t over 1. And to divide this whole thing by this whole thing, you take the reciprocal. And so that's going to be 2t cubed in the denominator. So d squared y dx squared. Let's multiply it with the numerator, the top numerator. So 6t times 2t is 12t squared. And then we have 2 times 3t squared, which is going to be a negative 2. So it'll be negative 6t squared plus 2, all divided by 2t cubed. So we can combine these two together. We'll get 6t squared plus 2 over 2t quantity cubed. Okay, so we could find points of what do you call those, points of inflection, where this actually goes to 0, but it turns out that because we have a positive here, we wouldn't have any real roots. Because if you think about it, if we set this equal to 0, we subtract 2 from both sides, we'd have 6t squared is equal to negative 2. When you divide by 6, you'd have negative 1/3. You can't take the square root of negative 1/3. So there are no points of inflection. And hence, there's only one direction this goes in because just a second. Actually, I'm thinking about this. You know, when t is positive, this is going to be positive. And when t is negative, this is positive. But since you have this cubed in the denominator, it's going to be positive when t is positive. It's going to be negative when t is negative. So you should have a change in sign due to the denominator, and that's going to change at t equals 0. So we'll go from negative, so it'll be concave down when t is less than 0, and it will be concave up when t is greater than 0, because this will be positive. Okay, and so maybe you can't do the same thing that we did when we had dx, when we had it just in terms of x and y. There might be some other choices where this thing goes to, which changes sign. So let's see if that happens or not. I don't remember from last time I did this, so let's open the graphing program and see what this thing looks like. So there we go, two-dimensional plot, parametric equations. The parametric equations are t squared minus t plus 2. So that, I'm doing 19 again, wrong problem. What's the problem I did? What problem am I doing? 37. So x is t squared, y is equal to t cubed minus t. We want to make sure we at least include 0 in there. So let's go from negative 2, t equals negative 2, to t equals positive 2. And let's put an error in it, t equals 0. So you can see here, this is where t equals 0. So we're going this direction. So t less than 0 is this part, which is concave down. This is t positive, so that's concave up. So let's see if that actually matches. So it's concave down to concave up. Okay, so we said when t was less than 0, we had concave down, which is what actually happened, and when t is greater than 0, it's concave up. So that is the final solution, the final answer to this problem. So what did we do? We found the first derivative as a function of t. We then found the second derivative as a function of t, which comes down to here. And to have a change in concavity, you have to have a change in the sign, going from negative to positive. And so a lot of times it goes to 0, and you can go on either side. But because this is an additional thing is in the numerator, and this is always positive, if we could see where this changes sign from negative to positive, then we're okay. And the issue was that because it goes vertical here, that's why it was more confusing than we normally have dealt with in the past. Because t equals 0, the second derivative would be undefined. It would be go to infinity, so it wouldn't tell us anything. So rather than going to 0, it went to infinity. It was not defined at that point. So there are two cases for points of inflection where the value is to 0, or where the function is undefined, which is in that case is true. Because when, yeah. Okay, so that's all we have to say about that.